In this section, we'll start discussing the three-dimensional structure, or as close as we can get to discussing the three-dimensional structure of the different solutions to the time-independent Schrödinger equation for the hydrogen atom, starting with the s-orbitals. But before we dive into that, I want to talk briefly about what I mean by the phrase orbital, or by the word orbital. Referring to the solutions to the hydrogen atom as orbitals takes its cues from the Bohr model. The Bohr model was this model that says that there's a proton in the center, and then the electron takes these fixed orbits of a particular distance around the proton. The Bohr model is a really beautiful model, which is unfortunately pure garbage. However, the term orbitals has stuck and is now used interchangeably to mean the eigenfunction for the hydrogen atom. So that means that when we're talking about the hydrogen atom, orbital and eigenfunction mean basically the same thing. And I and others use them pretty much interchangeably when we're talking about the hydrogen atom. There's a really important distinction though, which is that orbitals and eigenfunctions for many electron systems are absolutely not the same thing. Okay, so by many electron systems, I mean many electron atoms, so helium or lithium or anything else, or polyatomic molecules. Anytime you add a second electron in, these become conceptually very different quantities. Okay, so the orbital describes the spatial distribution of a single electron, but the eigenfunctions of the Hamiltonian are many electron systems. And so if you have an n electron system, these are functions of n electrons, whereas these orbitals are one electron functions. So while it's perfectly a-okay to use orbitals and eigenfunctions interchangeably when we're talking about the hydrogen atom or any one electron system, please do not make this mistake when you're talking about many electron systems. Okay, so now with that rant over, we can start talking about the three-dimensional shape of the actual hydrogen orbitals. So previously we talked about the radial distributions, but the radial distributions are only part of the story. To get the full picture, we have to also think about the angular distributions, or the orbital's orientations in 3D space. But the simplest types of functions to do this with are the s-orbitals, for the simple reason that their angular portions are constant. There's nothing interesting going on in them. So what I have here are the 1s and the 2s orbitals of the hydrogen atom. And so these are the complete eigenfunctions, and you notice there is no theta or phi dependence. And so basically we can pick any method we want to draw this, and we will get the same thing in any direction because, again, there is no angular dependence. So one simple way we can take to look at this is to just plot the value of the orbitals in the xy plane. And so what we're showing here is now a series of plots where what we have is a slice of the 2D plane. So this is the xy plane. So we have the x-axis maybe on the sort of bottom left, and then on the upper left we have the y-axis going. And then the height of this plot corresponds to the value of psi 1s here, or psi 2s here, or indeed those functions magnitude squared. Okay, so this is just taking this three-dimensional surface here, right? This is a 3D function because it depends on r, which includes x, y, and z. And what we're doing is taking a two-dimensional slice of it. So we're holding z fixed and changing both x and y. And so this corresponds to plotting the function psi 1s of x, y, and then letting z equal to 0. So it's equivalent to transforming these functions into x, y, and z, holding z fixed at 0, and then plotting x and y. And this is effective for the s functions because you can see these here already. There's no angular dependence on these. And so no matter which slice you took, whether you looked in the xy plane or the xz plane or the yz plane or any other weird combination thereof, you'd see the same exact thing. Okay, and from these you see that they all take their maximum value at r equals 0, but the value of that maximum shrinks as we go from 1s over to 3s, and you start to build in some radial nodes, which you can kind of see as dips here, but are much more apparent by looking at the magnitude squared of these, because these actually drop to 0. And this, you can see that there are shells here, right? So by looking at this, you can see that you have this inner part, which is large, and then you get a shell that corresponds to the bottom of this dip here, and you can see a mild buildup of a shell there. But then you can see actual shell structure in the 3s as well. So there's a maximum right at the nucleus, and then there's this other ring around here with some maximum, and then there's a final minor ring out at the edges. Okay, that's the s orbital. Next, we will talk about the p orbitals.